All right, so welcome back. Today in this video, we're going to be looking at some more mechanics of materials practice problems, and we're going to be focusing specifically on deformations. Now, if you missed prior videos, all right, I am currently in the reference handbook and going through each of the many topics that will be covered on the Civil FE exam. But if you missed shear and moment diagrams or stresses and strains, make sure you check out those videos. But in this video, we're going to be looking at deformation. So got some practice problems for y'all, and I want to dive right in. All right, so number one says, a steel beam initially at a temperature of 25 degrees Celsius is subjected to a temperature increase to 120 degrees Celsius. Okay. The steel beam has a length of 5 meters and a temperature coefficient of expansion of 0.000011 per degree Celsius. Okay. Calculate the total deformation change in length experienced by the steel beam due to the change in temperature. All right, so what information are we given? All right, we're given the temperature coefficient, temp coefficient, just gonna abbreviate, and I know that is our 0.00001 per degree Celsius. All right. Okay. I know that I'm also given a length. That's going to be 5 meters. I am giving a temperature, an initial temperature, 25 degrees Celsius, and a final temperature, just saying T0 is initial and T final is going to be 120 degrees Celsius. And I am asked to calculate the total deformation. All right. So to find this, I'm going to do a search, do deformation, and I'm going to be looking for something dealing with temperature. Right. It's giving me all these different. I saw something about thermal, so that's why I went back. Deformation, thermal deformations. Okay. Okay, so deformation caused by a change in temperature is noted as this weird S symbol of T, right? Okay, and that is equal to, right, this strange A component, which is temperature coefficient of expansion. Are we given that? Yes, we have a temperature coefficient. Do we have L, the length of a member? Yes, that is 5 meters. Do we have T, which is the final temperature? It's 120 degrees Celsius. And then an initial temperature, which is 25 degrees Celsius. So I know that this can be used. So let's solve. So the formula that we need is going to be this. Times L times T minus T 0. All right. So this component is my temperature coefficient, which is here. This component is here. My T components are both here and here. That makes sense. So let's go ahead and plug in. So we get times L, which is 5 meters. And this is per degree Celsius. So I know that per degree Celsius. Okay. Important to note those units of this coefficient. The coefficient of expansion is per degree Celsius. So, all right, times my 5 meters times my 120 degrees Celsius minus the 25 degrees Celsius. And so unit wise, Celsius, this is just going to be Celsius, and that's going to cancel out Celsius underneath. I'm going to be left with meters, which is what I want to be left with, all right? And so when I get my answer, I get 0.00525 meters. So I get A. All right, let's look at number 2. All right. So this one says, calculate the maximum deflection of a simply supported beam with a length of 4 meters and a uniformly distributed load of 200 newtons per meter. Elasticity is equal to 100. Oh, elasticity is equal to 100 newtons per meter squared, and inertia is 100 meters to the fourth. Cool. What information are we given? We are given length of the beam. We are given our uniform load, which is going to be 200 newtons per meter. We're also given modulus of elasticity, and we are given inertia, and we're trying to find we're also, there's one other thing. This is a simply supported. Just put SS, simply supported. Okay, and then we're trying to find max deflection. All right, how do I find that? Well, I'm just gonna look up deflection. There should be a chart that I can go to for simply supported beams that give me my deflection. Okay, so this is cantilevered beams. Don't need that. Simply supported beams. Okay, so deflection. Okay, so I know I'm in the right area. Max deflection though, so I'm looking for, deflection is denoted as V, right? But V max is what I'm looking for. So which chart would which formula would I choose from this chart, right? Well, this beam is a concentrated 1-point load at the center. This beam is a point not on the center. Okay. This has a moment going about the beam, no point loads. This one has a uniform distributed load across the whole thing. And then this one has a distributed load, but it's not uniform. It's going halfway. And this is a triangular distributed load. So we need a uniform distributed load, which is here, right? Is uniform across the whole beam. And so I know that we need to use this formula here. So formula needed is going to be V max deflection. Let's see if we have all the variables that we need. Okay, equal to -5 W L to the 4th over 384 EI. Okay. What is, so let's just write out our variables up top. And I'll just write them in red so they're big and bold. So W is equal to what? Okay, from our chart, W is the distributed load here. So what is that distributed load? Well, we know that W for us is going to be 200 newtons per meter. Okay, so we have W. What about L? Well, L, according to our chart, is the length of the beam. Do we have the length of our beam? Yes. You know the length of our beam is 4 meters. What about E? Okay, so E is always the modulus of elasticity of the beam. And we have that, which equals 100 newtons per meter squared. What about I? I is equal to the moment of inertia, which is 100 meters to the 4th. Okay, so now we have this variable, this variable, this variable, this variable. We have everything we need. So let's solve. All right. This is equal to -5 times my 200 newtons per meter times my L, 4 meters, all to the 4th, over 384 times 100 Newton per meter squared, and then multiplied by I, which is 100 meters to the 4th. All right, once you total all this up, we should get 0.066. What are my units? Well, when you get your units to cancel, your newtons definitely go ahead and cancel, right? So the only other unit is meters. And how do we know which unit it should, how many meters it's going to be? Well, we have up top, this is going to simplify to meters cubed. So you have on top meters cubed, and you have on bottoms, so you got meters cubed divided by on bottom meters squared. It's going to cancel to just be meters. So we have 0.066 meters, or 0.067 in this case for the answer, rounds up to D. Let's look at number 3. All right, so this one says, determine the maximum moment of a simply supported beam with a length of 7 and a point load of 300 newtons at the center. All right, so I think we're already in roughly the right area. All right, we are given the length of the beam, and we're also given that it's simply supported, or SS. We are given the load and the location of the load. So if I just draw this out, what does simply supported mean? Simply supported means your beam is going to be supported by, you guessed it, a pin and a roller. Great. All right. I know that from here to the end of my beam is going to be my length, which is 7 meters. Okay. And I know that my point load is happening right at the center. So it should be 3.5 meters and then 3.5 meters from the center. All right. Okay. And this load is 300 newtons. Okay. Anything else? Maximum moment. So we're trying to find max moment. All right. How do we get maximum moment? Well, you need to be in the right area first and foremost. So we need to be looking at a beam that is simply supported. So we are in the right section here. We need to make sure that that point load is at the center. This one is at the center. L divided by 2, L divided by 2. Which means it's at the center of the length. And then we also are looking for max moment, right? So we're going to find the maximum moment for this. It's going to be occurring at the center. And it's going to be, the formula that we need is M max is equal to P L over 4. What is P? P is equal to, according to our diagram, the load, which in this case is equal to 300 newtons. What about L? L is equal to the length of the entire member, which is going to be 7 meters. All right. So M max is equal to 300 newtons times 7 meters divided by 4, which equals 525 Newton meters, or B. All right, so this concludes the deformation section of the mechanics of materials review. In the next section, we're going to be looking at combined stresses, principal stresses, and Moore's circle.